All right, so just to reiterate, there's a typo in the gamma distribution handout. A chi-square distribution is a special case of gamma where alpha is r/2 and theta is 2. And so I made that fix, as you can see on the screen here, and that impacts problem 3, which I've rewritten the solution. It doesn't change, again, the answer. It changes what alpha is, what theta is, and then finding your value for r is going to still be 5. So the final answer doesn't change, just some of the notation does. We had finished the normal distribution last class. Nope, just checking. We went through all of the example problems here. And so remember, if x is normally distributed, you could convert your x into a z-score and find a probability with respect to that z-score. And where we ended last class was just an introduction to something called the Central Limit Theorem. And the Central Limit Theorem provides a means of converting a mean, a sample mean, into a z-score. And the formula looks similar. It's a subtraction on top divided by some quantity on the bottom. You've got mu in the top right, you have a sigma on bottom, but there's a little difference in that instead of x bar being transformed, instead of x being transformed, it's x bar, which is your sample mean. And instead of just sigma on the bottom, you have sigma divided by root n. And so it's a small but important distinction. Let's actually apply this so that you could see, how it differs from what we did on the last handout. And we'll just start with the first problem here. Cotton fabrics are often treated to improve their recovery from wrinkles after washing. However, the treatment tends to reduce the strength of the fabric. The breaking strength of untreated fabric is normally distributed with a mean strength of 57 pounds. So as I go through, I tend to write what's given. So I know mu is 57, and a variance is sigma squared, and this is 5.2 squared. Now that implies if I square root both sides, sigma is 5.2. We want to know what is the probability that the mean breaking strength of 6 untreated fabrics exceeds 50 pounds. So here is my clue as to what I want a probability of. Probability of the mean breaking strength, so that's x bar, of 6, so that's my sample size, which is denoted by a little n. Of 6 untreated fabrics, the probability that exceeds means greater than 50 pounds. And so that's my thought process. I'm talking through, how I'm reading this, how I'm pulling the information, how I know what the appropriate symbol is, because if I don't give it the correct notation, I'm not going to use it correctly or may not even use the right approach to solving this. Since this is a probability with respect to x bar, that is my signal that I need to use the central limit theorem here. And up top in yellow, I have what that formula is. So I'm going to convert x bar to a z-score and 50 into its numerical z-score, which is given by 50 minus the mean of 57 over sigma, which is 5.2, and that sigma is divided by the square root of n, which is the square root of 6. So now I need to calculate this. Again, 2 decimal places is pretty standard. And I get that this is the probability that z is greater than negative 3.30 when I round to 2 decimal places, because I've got negative 3.297 and change. And so rounding 2 decimal places, because again, that's what your standard normal table uses, this is the probability we want to know. Now, just as a warm-up, since we did lots of z-score probabilities last class, make sure you have your table and try to find what this probability is. Right? And I will give you a minute to refresh and try to do that. All right, so as usual, if you got an answer, feel free to post or say it out loud. I don't see any posts here on the chat board. You're looking for the probability that z is greater than negative 3.30. So Miku and Nan, you're similar. There's a subtle but important difference. Anyone know what it is? Oh, yes. Mm-hmm. Yeah, so it should be 0.9995. There's 3 nines. And that's because, again, it's good practice to do a sketch in case you're not really sure whether you subtract from 1 or not. And so negative 3.30 is over here, and we want all of this area. So if you looked up in the table and you got 0.0005 and stopped, if you drew a picture like this, you should ask yourself, does that only look like 0.05% of the area underneath? And hopefully your answer very quickly is no, that's a lot, which indicates that you need to subtract this from 1 in order to get the right answer of 0.9995. So if you haven't gotten into the habit just yet of doing a quick sketch of the standard normal, again, I do recommend that you take that step. Let me go to the table in case you forgot how to use the table. And so we're looking up negative 3.30, negative 3.3 you get from the first column. It's the second number from the top. And then the 0 for the second place comes from the column to the right. So you should see a 0.00 on top in that first row. You're looking in that column. And when you match that row and column together, you should see the value 0.0005. And so this is the area to the left, because that's what our picture says, to the left of negative 3.30. So that's another way that I can know and go back here and realize, oh, this is 0.0005, but I want the area on the other side, so I need to remove that from 1. So there's a few ways that you could have reasoned through in order to get at the answer. Let's take a look at the second problem. I know some of you may have started, and that's fine. It says, Charlotte is concerned that she may suffer from gestational diabetes. A patient is diagnosed with gestational diabetes if her glucose level is above 140 milligrams per deciliter 1 hour after ingesting a sugary drink. Glucose levels follow a normal distribution with mean 125 and standard deviation 10 milligrams per deciliter. What is the minimum level L such that the probability is 0.05 that the mean glucose of 3 measurements is above L? So there's 3 measurements, so that's my N. I want the probability with respect to a mean, so I want to know the probability that X bar is above L. We know that that answer is 0.05 because that's what's given to us. the probability is 0.05 that the mean is above L. So for this one, we want to work backwards in order to figure out what the value of L is. The way I think of attacking this after you set it up is to temporarily pretend that we knew L. So if we knew it, we would convert it to a z-score. We would say the probability that z is greater than, we would take L, we would subtract the mean of 125, we would divide by 10 over the square root of 3, and now we know that that answer should give us 0.05, that the probability should be 0.05. Now this I'm going to call z star. And what I want to know is, what should the value of z star be so that this probability is 0.05? So this is the area to the right. So I go to our now favorite table, and I'm looking for 0.05. Where in this table should I be looking for 0.05?
In the center part?
Yeah, in the center, the main body, because those are the probabilities. So you're looking for 0.05. You're not going to find it exactly, but you'll find it between 0.0505 and 0.0495. It happens to be perfectly in between those two. And those correspond to the z-score of negative 1.64 and negative 1.65. And so since 0.05 is right in between these two probabilities, I'm going to use the z-score that's perfectly in between negative 1.64 and negative 1.65. And so that is going to be negative 1.645. So the next step is to ask yourself, should it be negative or positive? Anyone have an idea?
Why is 0.05 between the two numbers?
I'm not sure I really understand that question. 0.05 is greater than 0.0495, and it's less than 0.0505. Do you agree with that?
Yeah, but wait. You're looking at 1.6?
Not yet. First, I'm just trying to find where is 0.05 within the probabilities of this table. I didn't get to the 1.6 stuff yet. Well, not at this point in the thought process.
So when you have the probability, you don't know what z is greater than exactly because you don't know what L is, but then the probability itself is 0.05. You have to look at this part of the chart as opposed to the way we were doing it before.
Yeah, because remember that first column and first row correspond to parts of z-scores, not probabilities. The main body of this table are probabilities, not z-scores. And so if you're looking for a probability, you have to be sure you're looking in the right section. Z-scores are not probabilities, they are distances. And so just to reiterate again, so you're looking for 0.05, which you know is a probability. This table, the main body of it, are probabilities, so you're trying to find 0.05 in it. You don't find it exactly, but you find it between two numbers. We actually find it perfectly in between, like the middle of these two numbers. These two probabilities correspond to the z-scores of -1.64 and -1.65. So if 0.05 is in the middle of these two probabilities, then a good estimate of its corresponding z-score is the z-score that's in the middle, or the average of those two z-scores. That's where I got the 1.645 from, is I went halfway between 1.64 and 1.65. And so the question I left you off with is, should it remain negative or should it be positive?
Should be positive.
Why? And whose voice was that?
Miku?
Hey, Miku. Why positive?
Hi. I'm just thinking because, you know, the probability is 0.05. So if it was negative 1.645, it'd be much bigger.
Mm-hmm. Yeah, so if you draw a horrible sketch like mine and you put negative 1.645 here, and that is supposed to be plugged in for that z star. So z greater than that value, that's all of this area, which is definitely larger than 0.05. And so that implies that we really want the positive value, which is going to correspond to the area in this region, which is small. And so that's one way to deduce that this is the right z-score that we want to use. So now, from this point, we're saying that this fraction, this ratio that I've got for the z-score needs to be 1.645. So set L minus 125 over 10 over root 3 to that z-score value. And from here, it's algebra to solve for L. So when you do that, you should get about 134.5. That's rounded a little bit, but it's close. $134.5. Make sure that you're actually able to get that, you know, that you're manipulating correctly. You should multiply 10 over root 3 onto the right, then add 125. And so you should be larger than 125 for your final answer. Anyone not getting it? Or any questions about the reasoning? Okay, I'm not seeing anything on the chat board, so I'll continue to problem 3. Problem 3 says an automaker of mid-sized cars claims that the distribution of mileage for all their cars is normally distributed with mean 33 and standard deviation 2.7. What is the probability of the automaker observing a mean MPG of 31.2 or less based on a random sample of 20 cars? I want to give you a couple of minutes to see if you're able to solve this problem on your own. All right, you've seen one similar to it. You're welcome to compare it to the comparable one on the normal distribution handout to be able to distinguish why they differ. But I just want to give you some time to see how much progress you can make on your own for question number 3 on this handout. So I'll leave this up. I'll pause the video or the recording, and I'll come back in a few. Go through. All right, so you've had a minute or so in order to work through this, and your process should have been maybe to reread it again, and then as you go through, you write down what you know and the appropriate notation. So we're told that the mean is 33, and since it's written very broadly, and the mileage for all their cars, I know that's about the population, and the standard deviation is in the same sentence, so that's also about the population, so that's a sigma symbol. That's 2.7. Later on in the last question part, I learned that the sample size used was 20. And what I want to know is, what is the probability of the automaker observing a mean less than or equal to this value? So I want the probability that X bar is less than or equal to 31.2. When you convert this to a z-score, it comes out to negative 2.98. And this is a less than probability. It's a negative z-score, which is exactly what that table gives you directly. So there's no manipulation required. When you look in the table, you should find 0.0014 as the probability from that table. Let me switch to the table for a moment just to go through that. So we're looking for negative 2.98. So you're looking for the row with negative 2.9, and you're going across to the column with 0.08, which should bring you to this highlighted value of 0.0014. And that's your answer. If you're not sure whether to subtract it from 1 or not, again, you could go back and you could draw a picture. Your picture should look something like this. And the area we're interested in is this small piece to the left. So it is pretty small, and having a small value seems reasonable. It wouldn't make sense to subtract from 1 and have an answer of around 99%, because that 99% is a whole lot, and this shaded region is very little. So again, if you are finding that you're not sure whether to manipulate it, get used to drawing sketches like this and understanding how to utilize them in order to be able to make that decision.
Wait, why is the standard deviation? I just got confused with the word. So the standard deviation is the variance?
Standard deviation is related to variance. Just like in problem 1, what were we given?
The variance.
The variance. And the variance is denoted as a sigma squared symbol.
I thought it was a sigma.
What's that?
I thought it was a sigma.
That's standard deviation, which is what I got next.
Oh.
So in short, standard deviation is the square root of your variance, which is why your notation is sigma for standard deviation, and variance is sigma squared. So that's what
That's for everything, right?
This will always be true, yeah.
Okay.
And so that's what I did over here. I knew I needed sigma, not sigma squared. So to get rid of a square, you square root it. Sydney, did that make sense?
Okay.
All right. Before we continue on, we've gone through 3 problems. I know just a handful left chat messages that they were able to do 3. Hopefully quite a few more of you were able to make progress on that one. any questions before we continue with the remaining problems on this handout? Any questions with what we've done or any of the reasoning? Okay, well, as usual, I will take that silence for that you guys are all doing all right. And I will move on to problem number 4 here, which says the weight of adult males is normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. An elevator at a men's fitness center has a sign that says that the maximum allowable weight is 4,700 pounds. If 25 randomly selected men cram into the elevator, how likely is it to exceed the maximum allowable weight? So over here, you may start this the same way we've done previous ones, and that is by writing down what's given. So we know the average male weight is 172 with a standard deviation of 29. We are given later on that we're looking at a sample size essentially of 25. And then you've got this 4,700 pounds. What is that 4,700? Is that a mean?
Would you have to divide it by 25 to get the mean of each person?
Oh, great job, Miku. So Miku kind of jumped ahead from where I wanted to lead you guys, but that's okay. And so essentially what she realized is that this problem is asking what's the probability that the sum of all the weights of the people on the elevator exceeds 4,700 pounds. And that's literally what's given. You have a total weight, and if you had 25 people who were kind enough to tell you their weight, you would add that up to know, is it over 4,700 pounds? Now, based on this handout, we want to convert an X bar to a Z-score. We don't have an X bar, but we can get at it, which is what Miku got to. And she said, well, you know, to get an average, you add up everything and you divide by the number of values you added. Here we have the add up. So in order to convert this, we need to divide by the number of values that we added, which is 25 weights, which means that this probability is the same as the probability that X bar is greater than 4,700 divided by 25, which is 188. So now we are in a place that we've built some comfort with because we've practiced twice now finding the probability of a mean. And so from here, what are you going to do? Find the z-score. And so Nan, what is your first step to finding the z-score? You take 188 and you do what to it? Yep, you subtract 172, which is the mean, and then divide by that is correct. So 29, which is the standard deviation over the square root of 25, which is one that you should all be able to do in your heads. And now you can calculate what that z-score is. And you should get 2.76 to 2 decimal places again. And then you go to your table and figure out what that probability is. So go ahead, go to your table and see if you can get the right answer for the probability. All right. Again, I'll pause for a moment. Should just be a few seconds. Okay, so does anyone feel that they have determined what the probability is? This is problem 4 that we're working on. So I have a vote for 0.0029. Any others? Anything different? Same from Sydney with 2 Y's. All right, so let's draw a picture and just see if it seems reasonable. So in our picture, it should look something like this, where again, it's standard normal, it's bell-shaped, 0's in the middle. You've got 2.76 as your z-score plotted appropriately on the x-axis there. And the probability is the area to the right of that, which is a small region, so we should have a small answer. And when you go to your table and you look up 2.76 or the negative value of it, you should find 0.0029, just like the lady said. And that's the right answer. There's no reason to subtract it from 1. Tackle number 5 now on your own. All right, I'm gonna pause the video, the recording again. I'll give you a few minutes. This one you should be able to do from scratch. And if you happen to finish pretty quickly, feel free to try your hand at number 6, but we'll get there in a few. All right, so I know hopefully most of you finished problem 5 here. And again, you were, a number of you, and as far as I know, 1 guy, were able to get to the answer. So let me go through it just to either help you build confidence or show you how to do it. And so as you read through, you learn that the mean salary is 62,000 with a standard deviation of 32,000. There's 100 employees. And we want to know the probability that the average exceeds, which is greater than, 66,000. When you convert this into a P statement using a z-score, the 66,000 becomes 1.25. And by symmetry, this is the area to the right of 1.25 is the same as the area to the left of negative 1.25, which when you look up in the table, you get 0.1056. So about 10.5% is the probability that the average of 100 employees will exceed 66,000. And that's it. Problem 6, a little different. So before you get to that, I'm going to throw the opportunity out there once more. Any questions on anything from 1 through 5 on this handout? All right, so let's take a look at problem 6 here. It says, let x come from a distribution with PDF f of x equals x cubed over 4, where x has the support from 0 to 2. So x is not normally distributed, which is different from all the previous problems we've done. A random sample of 25 observations, so here's our n, is drawn from this distribution. We want to determine that the probability of the mean is between 1.5 and 1.65. And so for this problem, the way that I think is I first go to what is it I want to find, and that is the probability of an average. As soon as I know it's the probability of an average, I think of Central Limit Theorem. And the Central Limit Theorem says that X bar can be converted into a z-score. But in order to do that, I need to know mu, and I need to know sigma. Let's start with mu. How can you get mu? Because it's not directly given in this problem. Anyone have an idea? What is mu equal to?
The expected value.
The expected value of X. The expected value of X. So then you go back to a continuous scenario, and we know we need the expected value of X, and so that means we need to integrate X times the PDF. So mu is the first moment. Expected value of X is the integral of X, what's inside your expectation, times the PDF, which is X cubed over 4, and the support is 0 to 2. So when you integrate this, that's X to the 4th over 4 becomes X to the 5th over 4 times 5, which is 20. And you evaluate from 0 to 2. 2 to the 5th, you got 2, 4, 8, 16, 32. Divide by 20, which happens to simplify nicely into 1.6. If it didn't come out to a relatively nice number, I'd leave it in fraction form, but this one happens to work out nicely. So now we have mu. We're missing sigma, but we need sigma squared, or at least we could get sigma squared, which we could then use in order to get sigma. I just chatted how to get the variance. How do you do that?
The second moment minus mu squared.
Mm-hmm. Yeah, so it's going to be the expected value of X squared minus mu squared, which is 1.6 squared. So what we need is that second moment. So let's continue with that for down here. So this is the expected value of X squared, which by definition is the integral from 0 to 2 of X squared times the PDF, which is X cubed over 4 dx. And so it's the integral of the function inside the expectation times the PDF. That is the definition of expected value. So the integrand is X to the 5th over 4. When you integrate this, you get X to the 6 over 4 times 6, which is 24. We know 2 to the 5th is 32, so multiply by another 2 to get 2 to the 6th gives you 64 over 20. And this simplifies to
sorry, 64 over 24.
Well, yeah, thank you. So that simplifies to 8/3. I wouldn't write it as 2.67 just because some of that rounding might throw the final answer off. 8/3 isn't that bad of a fraction to use. So
could I ask a quick question? Okay, I don't know if this is just for discrete, but could we not have taken the derivative of the first moment, like x to the 5th over 20, to get the second moment?
I think you're thinking of the MGF.
Oh, okay, yeah, my bad.
And you could get the MGF for this function. It would require 3 rounds of integration by parts, which you may not enjoy doing.
Okay.
But you can. And then once you have the MGF, you could take derivatives in order to get the first and second moment.
Right. Okay. Yeah, thank you.
Another path. I don't think it's the easier path, but it can be done.
Okay.
It could be good practice. I'd say on the side, now that you know what the answers are, you could see if you could do it from the MGF route also.
Okay, thank you.
You're welcome. So then I'm going to go back here and plug that in. So you've got 8/3 minus, so 1.6 is, I want to put that into a fraction form. That's going to be 8 over 5 squared. Which you've got 8/3 minus 64/9, which is going to be 24 minus 64. Something's off. Three. What did they do wrong? Oh, okay. That's what I did wrong. Sorry, I rushed it a little bit. This is 8/3 minus 64/25. And then I'm going to use 75 as the common denominator. So that means you got 8 times 25. Or 200. Minus 3 times 64. Which is 192. And that comes out to 8 over 75. And that's our variance. Which, when you square root this, you get the standard deviation, which is about, I'll do this to 4 decimal places, 0.3266. So now we have mu, we have sigma, we have n. Now we could actually apply this information in order to find the probability at hand. So, probability that x bar is between 1.5 and 1.65 is the same as the probability that z is between, and we're going to get the 2 z-scores, one for the left side, one for the right side. So I'm getting negative 1.53 for the left. And 0.77 for the right. All right, I'm going to pause again because this is our first area between on this handout. So I want to give you, a minute to see if you can get this probability again using your standard normal table. All right, so I've seen some answers and questions roll in, and the answer should be 0.7164, which I see at least one person got. Another person had the right idea for one manipulation that you might make. It's not the only one, but I'll do it through that path. And so the area between these two values is the same as the area to the left of the bigger value, and then removing the area to the left of the smaller value. Using your standard normal table, the area to the left of positive 0.77, you would get from 1 minus 0.2206. Tony, I'm not sure if you saw that, but that's a manipulation that you'd have to make. The area to the left of negative 1.53, you get directly from the table to be 0.0630. And then when you actually calculate this, you get 0.7164. And that's it. We've gone through all the problems. We have finished our continuous section of this course. So we've done distributions for discrete data, for continuous data. And as I told you last week, we're about to move on to bivariate data, which we will start this lesson. But before we do, any questions on what we've covered so far? Tony, do you understand where you went wrong? Okay. All right, so again, that concludes the continuous part of this course. It's not the last time you'll see integrals. You're about to use them again in this next aspect. And now we are faced with a scenario where you may have a distribution that is no longer two-dimensional, because you've seen uniform, with an XY axis, you've seen the normal distribution with an XY axis, the standard normal, but now you have two variables. So this may be a distribution of heights and weights, or of age and salary. So in this case, I tackle discrete and continuous simultaneously now that you've seen both, one at a time. And you have the similar criteria that you need to satisfy. If it's discrete, each of your probabilities must be between or equal to 0 and 1. So that's the first criteria here. And the sum of all of your probabilities must be 1 or 100%. So it's not that different. Notation changes a little bit, but the concept is the same. And it also follows in your continuous scenario, the distribution has to be at or above the x-axis, so non-negative. And when you get the area under the curve, it has to give you 1 or 100%. And so those are the criteria that have to be satisfied. Again, you've seen similar things in the one variable discrete and continuous cases. Now we just have 2 or more variables. Most of it's going to be 2 variables. Some other concepts that are new are that if you, let's say, have 2 variables and you sum up across one of them or integrate one of those variables out, you end up with a function of just one variable. So originally what you had is a joint PDF or joint PMF. I'm looking here, joint PDF or joint PMF. And when you integrate one of those variables out, you have what's called a marginal distribution, or marginal PMF or marginal PDF, depending on whether it's discrete or continuous. And so it's some terminology that's being introduced here. Joint, because you are essentially joining 2 or more variables. Marginal, because you have marginalized it by removing one of the variables. If X and Y happen to be independent, it's a really neat property because then you have the multiplication rule. And this is true whether it is discrete or continuous. If you have independence for discrete distributions, then the joint distribution is equal to the product of the marginals. If you have it for continuous distributions, then the joint distribution is equal to the product of the marginals. So the idea holds whether it's discrete or continuous. And you'll see we'll likely make use of this in this handout. So let's start practicing this. Again, this is just an introduction to some notation and concepts, but I think it'll start falling into place as we start doing. In our first problem here, it says, let the joint PMF of X and Y be defined by this distribution, that the probability of X comma Y is given by X plus Y divided by 21. And X can take the values of 1, 2, and 3. Y only can be 1 and 2. Is this a discrete or a continuous distribution? Miku, how do you know it's discrete?
Because they're all integers.
Yeah, so you have a finite number of values for both X and Y. So this is a discrete distribution. The other hint, which is just because of my notation, is that I defined it as a capital P of. And so I use capital P for discrete and little f for continuous. So it's some notation might give that away also, but there's a few ways you could have deduced that. We want to determine the marginal distributions and show that X and Y are dependent. So let's first start with finding the marginal distributions. To get the marginal distribution of X, so we want P of X, that means we need to sum out all of Y. And Y goes from 1 up to 2. So we are summing across Y. And our joint distribution is X plus Y over 21. Now remember, again, we're summing across Y. So when Y is 1, we have X plus 1 over 21. And then the sum, the sigma, capital sigma notation means add. Now when Y is 2, so that's going to be X plus 2 over 21. And these have a common denominator, and so adding the top gives you 2x plus 3 over 21. And x remains the same as being 1, 2, or 3. And so that is the marginal distribution of x. Since this is a relatively simple and direct one, try your hand at finding the marginal distribution of y. I'm not going to pause the video here. I'll just, let it be silent for a bit, just because I anticipate many of you will get it pretty quickly. When you think you've got it, feel free to either call it out or chat it. Yeah, no, that's perfect. I know what you mean. I would put the numerator in parentheses if you're writing it like that, but I know what you mean. And so Nan said, okay, let x be 1. So you've got 1 plus y over 21 plus x is 2. So 2 plus y over 21. And then when x is 3, you have 3 plus y over 21, which when you add the numerators, because you have a common denominator, you get 3 plus 2 plus 1 is 6. Y plus y plus y is 3y, all over 21. And if you wanted, you could factor out a 3 on top and bottom and simplify. I'll do that here. It's not required, but you could view this as 2 plus y over 7, where y can be 1 or 2. And so here are your two marginal distributions. How can you check to see if they might be feasible? What I would do is I would see, are they valid distributions? Because even though they're marginal, remember they're actually marginal distributions. So they still have to satisfy criteria you've learned in the past, which means that their probabilities have to be non-negative and between 0 and 1, which they will be because it's all positive values that are there, positive values that are going in. And that the sum of all the probabilities must be 1. So just to demonstrate for the marginal of y, if I find the probability of 1, that's going to be 3/7, plus the probability of 2 is going to be 2 plus 2, or 4/7, which is 7/7 or 1. And so that is a valid distribution, which implies I likely did not make a mistake, right? So it's a quick check to see, like, did you possibly make an error and it's not even a valid distribution? That's the point I'm trying to make, at this moment. So we've got our two marginals, and now we need to show that they are dependent, which means we want to show that they don't satisfy the independence criteria. On the left, P of x comma y is given as x plus y over 21. We want to know, is this equal to P of x, which is 2x plus 3 over 21, times P of y, which is 2 plus y over 7, if you use the simplified form. And no matter how you try to manipulate this right side, is it going to ever equal x plus y over 21? No. And so this doesn't hold, which means that X and Y are dependent. So that's what this problem was looking for. It had three parts. Find both marginals, Px and Py. I kind of view that as two separate pieces. And demonstrate that the criteria for independence isn't satisfied, which must mean that they are dependent. Let's practice some more and take a look at problem 2 here. It says, let X and Y have the joint PMF. So that's a hint, PMF, that's implying discrete. And that PMF is X times Y squared divided by 30, where X can be 1, 2, 3, and Y can be 1 and 2. It just happens that the support is the same as problem 1. It's not required to be so, but it is for this problem. We want to deduce the marginal distributions. So again, deduce, derive, create, find, and determine if the variables are independent or not. So this is asking for most of the same stuff that we just did. It's also asking for you to compute the mean of X. So ignore that last task. Having gone through 1, I want you to try to do the same thing, but now for problem 2. So you need to get the marginals, and you need to show whether they are independent or not. I'm going to pause the video, give you a few minutes to see if you could do that part on your own. If you happen to finish that quickly and you want to try to come up with the mean of X, then feel free to do so. You've got the knowledge to do that. You just haven't seen it done in the bivariate case. But again, I'm going to pause and we'll return in a few minutes. All right, I'm going to call on people here just to try to get feedback from some others that aren't really participating. Aaron, do you have the marginal distribution for Y? Again, you could either type it or take yourself off mute in order to say it. Either's fine. Aaron, you there? So it sounds like you checked if it's a valid distribution. I think for your whole the joint distribution is what I'm guessing. Did you happen to get a functional form for P of Y? Okay, and what was that function? All right, I don't know if you're making a correction or if you're working on it now, but I'm gonna call on Alvin. Alvin, did you happen to get the marginal distribution for X?
For P of X, I got X over 6, where X could be 1, 2, or 3.
Perfect. All right, so let's start with that one. And in the meantime, Aaron, you're welcome to try to figure out why while I'm demonstrating the P of X one here. So the marginal of x, or p of x, again, because this is discrete, you are summing across y. So y can be 1 up to 2. And the joint distribution is x times y squared over 30. And so evaluating y, at 1, you've got x times 1, or 1 squared, over 30, plus x times 2 squared over 30, which combines to 5x over 30. And if you simplify, you get x over 6, with the support of x being 1, 2, and 3. So that's perfect. I trust that's how you got there, Alvin. And that's exactly what you should have. Again, it's not required to simplify. I think it's pretty easy in this case to do so, but that is the equivalent of what you should have. Aaron, did you happen to figure out the marginal of y? I'm just setting it up, but if you have the answer, feel free to let me know. Y up to. So it's going to be different. Other than being a ratio, it's not going to end up being x over 6. Arnold, did you happen to find the marginal of y?
Sorry, can you repeat that?
Did you find the marginal distribution of y?
Oh no, still doing the work.
Okay. What about you, Jay? Jay, did you get an answer for p of y? Jay, remember you're muted. I don't know if you're trying to say it, or you could always write it if you want. And yeah, that is what you should end up getting. So he got 6 times y squared over 30, which you could simplify to y squared over 5. And I'll finish the solution that I started here. So now you are evaluating x. So when x is 1, you've got y squared over 30, plus when x is 2, you have 2y squared over 30, plus 3y squared over 30. And that's it for what x can be, 1, 2, and 3. With a common denominator, you've got 3, 5, 6 y squares over 30, which simplifies to y squared over 5. And again, y can only be 1 and 2. So those are your marginal distributions. In step 3, you can check p of x comma y is x times y squared over 30. We want to know, is this equal to x over 6 times y squared over 5? And that is your px times py. Is the left side equal to the right side?
Yes.
Yeah. So this is true, which means, what do you know about x and y?
They're independent.
Mm-hmm. Yeah, x and y are independent. And so those are the 3 steps that we went through in problem 1. You got to practice it here on your own for problem 2. There's one more detail that this problem is asking for, and that is to compute the mean of x. And so based on what you've learned, you know that the mean of x is asking for the expected value of x. And the expected value by definition is the sum, but now because this is a joint distribution, it's a double sum. of x times your PMF, which is pxy. Now I'm going to play with this before I actually start solving, because I want to demonstrate a shortcut for you guys. The first summation that I wrote here is y, or the first one closest to your x pxy is y. The x that's being multiplied in has nothing to do with the y, so I can actually pull that out That's not a product. I know I wrote the product symbol there, but I could pull it out here and rewrite the double summation in this fashion. What do you get when you sum across y of your joint distribution? What is that equivalent to? You did it above. When you plugged in all possible values for y and you added up, you ended up getting P of what? Yeah, P of x. And so when you sum out y, there's no y's left, and you're left with a function of just x. So this is P of x. And what's neat is that you now have a form that you guys have seen before that's less complicated. This is just the basic expected value formula that you've used in the past with the discrete case, the sum of x times the PMF. And you have P of x, which you just found. So this is summing for x is 1, 2, and 3 of x times, and the marginal distribution of x is x over 6. So that's, you're summing x squared over 6 for each x value. So that's going to be 1 squared over 6 is 1/6, plus 2 squared over 6 is 4/6, plus 3 squared over 6 is 9/6. With the common denominator, this is 14 over 6, which gives you a mean of about 2 1/3, or 2.33. So that's an example of expected value in the bivariate world for discrete. We've gone through 2 problems in this. We have time to continue and maybe get through 1 more. I don't know about 2, but any questions on the 2 that we've done so far?
Wait, so P of x comma y in this case is P of x?
The sum of P of x, y across all y values is P of x. So when you sum out one of the variables, you're left with the other one. My curly bracket includes the y summation.
Wait, because you have x P of x, right, for the mean. And P of x is P of x comma y, but you're only using P of x because...
No. So the definition of expected value is where I start. I'm double summing x times the joint PDF. But the closest summation that I'm going to act on is the sum over y. This x has nothing to do with y. It won't be changing over that first summation. So I'm allowed to pull it out of that summation, the sum over y, which is what I do in the second step. I brought this x out of the summation across y. And what I realized is that the summation on the right, the summation across y of p of xy, is the marginal of x. I'm looking here. That is the marginal of x. And so this becomes the sum across x of x times p of x, which is my next statement. So I went from a double sum to a single sum across x only.
Wait, so you pull on x. Wait, so why do you pull on x again?
Because it has nothing to do with y. And that summation is only changing y.
Wait, why is it only changing y?
Because that's what it says. This is the sum over y values.
Wait, is that the equation? I'm sorry, not the formula, whatever, where it's like you summing over y of p of x, y or something?
That is the expected value of x when you have a joint PDF or joint PMF.
Expected value of x with joint PDF.
It's the same logic that you did in the one variable case. You have a summation, you've got what's inside your expected value, which in this case is x, multiplied by the PMF that you're working with. And so the form is exactly the same. It's just because you have two variables that instead of a single summation, you have to have a double.
This is PDF.
PMF, because this is discrete. If it were
okay.
PDF, then you'd have a double integral, which you will see in the next one.
So you pull out x because it's not summing over x.
Mm-hmm.
Okay, but why is p of x comma y equal to p of x?
It isn't. I didn't say it is. I didn't highlight only p of xy, Sydney. What did I highlight? In yellow.
The sum of it?
The sum of p of xy across all y values. That is, as I highlighted and underlined in red, is the definition of a marginal distribution, and in particular, the marginal of x. So I'm very particular with how I wrote it. All right, it's all right there, and it all flows.
Okay.
All right, let's take a look at problem 3. I think we'll be able to finish it in its entirety, but we'll do whatever we can. So this is the first case where you have a joint PDF, which means that this is continuous, not discrete. But it also has a support where x and y are dependent on one another. So there's not one support for x and a separate one for y. If you look at it, x is greater than 0, but it's less than y, and y is less than 1. And so you have to actually take that condition into consideration. And you'll see that as we go through figuring out marginal distributions. So let's go and start that. Let's take the marginal distribution of x, which means we need to integrate out which variable? The what?
Y.
Uy, yeah. So now we need to figure out, well, what is the support of y? And looking at this, it's clear that it can't be bigger than 1, but its lower bound is x. So y is bounded by x and 1. And so this is what we want to integrate. It's at this point where I'd actually plug in what the joint distribution is. So we're integrating from x to 1 to dy, because 2 is your joint distribution. Integral of 2 is 2y, because again, you're integrating with respect to y. And you are evaluating from x to 1, which is going to be 2 times 1 minus x. And x has support 0 to 1. So you would no longer have y in the support because we just integrated y out. And now we're going to use a similar process. Starting from scratch, we want the marginal distribution of y. So we're integrating 2 dx because we're integrating x out. Anyone have an idea what the bounds of the integration here should be?
Is it 0 to y?
Mm-hmm. Yep. So x is greater than or equal to 0, and it's going up to y, because again, you're starting over, so you're starting from the joint distribution. And when you integrate this, you get 2x, which you are evaluating from 0 to y, which comes out to 2y. And y has the support 0 to 1. Again, you no longer have x in there because we integrated out. How can you check that these work? What might you do? So what should come to mind is check the criteria. There's supposed to be distributions. If you did everything correct, and it's usually not the integration that causes people problems, it's either the limits or defining the support. And so the distribution of y is the easier one to do in your head. The integral of 2y is going to be y squared. And when you evaluate that from 0 to 1, you get 1 squared minus 0 squared, which is 1. So it satisfies having the area underneath be 1. And you'll find the same is going to be true for your marginal distribution of x. If you integrate 2 times 1 minus x over 0 to 1, you will end up getting 1. You also need to check that they're non-negative. 2y is a line with slope 2. And from 0 to 1, it is going to be non-negative. 2 times 1 minus x is also a line with negative slope. But from 0 to 1, that's also going to be non-negative. And so it's very quick to check, might I have made a mistake? And so far, these two functions are valid distributions. So it seems like we didn't make a mistake. So that is it for part A. For part B, we want to compute the means. So let's get the expected value of x By definition, this is the double integral of x times the PDF, which is 2. And we could do, it doesn't matter whether you do dx dy or dy dx, you could do it in any order. I'll do dy dx. So integrating over y first, we're going from x to 1, and then the second integral will be 0 to 1. Have you guys done double integration in the past? I'm not sure if it came up in one of your calc sections or maybe a different course. Yes? Okay, because I'm not sure if I knew single integrals you had to see, but I wasn't sure about double integrals. And so you could either evaluate this, or you might recognize that it's actually going to be the integral of x times the marginal of x, which is a nice shortcut, but this is a pretty simple one to do. So you're going to get 2 times x times y when you integrate with respect to y first, and you're evaluating y from x to 1.
Wait, what's a double integral? I don't remember learning this.
It's when you have a function that has 2 integrals instead of just 1. So you have to integrate 2 times, starting from the inner integral going outwards. So this is going to be 2x times 1 minus x. So notice that this is, I started from scratch, but it's useful to recognize that this is x times p of x. And so when you integrate this, this is going to be x squared minus, that's going to be 2x squared, which is 2/3 x cubed. Evaluate from 0 to 1, which is going to give you 1 minus 2/3, or 1/3. So this is the mean of x. Now you want the mean of y, which means you want the expected value of y. And from here we could take the shortcut. So this is y, the integral of y times p of y. And in this case, we know we're integrating from 0 to 1. So this is the integral of 0 to 1 of y times, sorry, that p should be an f. Of f of y is 2y. So that's going to be 2y squared when you multiply by the y. And when you integrate this, you get 2/3 y cubed. Evaluate from 0 to 1, which is 2/3. So we've got the mean of x and the mean of y. And it's good practice for the mean of y if you start from scratch. So like we did for the mean of x, just to see that it works out, you know. So I did it from scratch for the mean of x. I used the shortcut for the mean of y, but it's good practice to be able to, you know, do it from the first principles per se. Part C asks us to calculate the variances. So to do that, we need the second moment. So I need the expected value of x squared. I'm going to use the shortcut here. This is integral from 0 to 1 of x squared times the PMF of 2 times 1 minus x. So the integral of 2x squared is 2/3 x cubed minus the integral of 2x cubed is going to be 2x to the 4th over 4, which is x to the 4th over a half. I simplified. and you're evaluating this from 0 to 1, which is going to give you 2/3 minus 1/2. And when you get a common denominator, you get 4/6 minus 3/6, which is 1/6. And since we want variance, the variance of x, I'm going to put a subscript here, is given by the second moment minus the first moment, which we got to be 1/3, and the 1/3 is squared. So this is 1/6 minus 1/9, which is 9 minus 6 over 54 when you get a common denominator. So that's going to be 3 over 54, which simplifies to 1/18. With only a minute to spare, I'm going to leave it to you to figure out the mean, or the second moment of y, and thus its variance. But I just want to introduce what you would use in order to answer part D. So correlation is going to be given by the expected value of xy minus the expected value of x times the expected value of y over the standard deviation of x and the standard deviation of y. And so with this formula, you should actually be able to answer this because we just got the variance of x, so you know how to get standard deviation from that. We have the expected value of x, we have the expected value of y. You should be able to get the standard deviation of y. It's a similar pattern to what we just did in part C for x. And then the only really new thing that you've never done is the expected value of x times y. But that would be just like what we did here, except instead of having an x, you'd have an x times y times 2 inside this integral. So that's really the only difference there. So what I'd like for next class, just so we could start off running, is I want you to try to complete parts C and D. You're welcome to give 4 a shot, but I'm happy to continue there for next class. But at least try to finish parts C and D here, just so we could do those quickly and then move on with this worksheet. Any last minute questions?
Wait, C is, you have to calculate E of y squared?
Yeah, because you need the variance of y. So C is not done. We got the variance of x, but we didn't do the variance of y, so I'm leaving that for you to do. And the variance of y is going to use the second moment of y. Anyone else? Any other questions?
Wait, the variance of, we haven't, so wait, E of x, y, that is related to one of the other problems, right?
That's
But
part.
you said you do it slightly differently.
So this is what you're going to use to get the variance of y. You already have the second term, E of y, you just need the second moment. And then E of xy is the only thing that you've never seen before, but you have the background in order to be able to get it. And so I want you to give it a shot to try to finish parts C and D. All right. We're a little past our time. Have a great weekend, and I will see you all again on Monday.